Awesome, thanks so much. Before I start that, I probably want to apologize because this is a pretty old result by now. It's about 5 years old and has been superseded by a lot of things that people have actually been talking about here at the conference. The original result that I actually wanted to talk about, some work with Pavel, is unfortunately we didn't finish in time, so I'll have to back up and go to this. But since we've discussed a lot about this, it might actually be interesting to some people that I talk about that. So exactly, so what I'll talk about is sort of an algorithmic take of some version of quantum detail balance that allows us to implement Szegedy walks. So maybe for starters, I should explain what we want to do. So a Szegedy walk, high level, is someone comes along and gives you sort of a classical Markov process. It's a reverse, so detailed balance classical Markov process. And what you want to do, so what Mario Szegedy did is basically he transformed that classical walk into a unitary that implements some form of a quantum walk that has very, very nice properties. Okay? I'll talk about that, introduce that in a bit of what that walk does and what the features are that are so desirable for those unitary walks. And so our question is essentially, okay, suppose you start even quantumly first, say, and you don't start from a classical Markov process, but you start from a Lindbladian or some TCP map. Is there also some form of a Szegedy walk unitary that is completely unitary that you can associate with that Lindbladian or that TCP map walk? Okay, and so the question is, can you construct that? What are the caveats and so forth? Because I remember when I was a grad student, that's what people often discuss, and it was kind of challenging to come up with a clean form of how to write that and how to construct that. Okay, so that was the goal. So let me first go and review what you want from a Szegedy walk, and review a classical Szegedy walk. So as I said, we're given a classical walk matrix, the stochastic matrix P. So the unitary that you associate with that has sort of one property has an eigenvalue 0 or a phase gap, eigenvalue 1 or a phase gap of 0 with the quantum state that is sort of the Q sample and is associated to the limiting distribution of that walk. Moreover, you have sort of this quadratic speedup in some sense by basically taking, if you look at the spectrum of the walk, you basically map that to the unit circle because it's a unit. But then what you have in mapping that to the unit circuit, you basically get a quadratic spread. So initially, if you had a gap delta, you can basically go now and have like a phase gap of square root of delta. So you increase the gap by a little bit. And so what we want is sort of something similar, and there's a lot of like Pauli speedups in classical quantum walks where it's helpful. It's helpful to have these constructions for other parts of algorithms, and these properties come in very desirable. In general, we don't really care that much about square root speedups at the moment anymore. So you want typically more, but structurally, it's very, very interesting to look at those, and they're sort of very interesting building blocks for more general algorithms. Okay, so. Typical picture we work with, it's sort of finite state space. We only consider ergodic Markov chains. We have a stochastic matrix, and we assume it has a stationary distribution pi. So I'm assuming I'll run through that part very quickly, because everyone knows that very well. However, then what's important to us is sort of, okay, so this is when we talk about convergence, we loosely speak sort of just in terms of spectral convergence here, and the speedup is likewise also only in spectral convergence, because that's what you basically amplify the gap, right? And so then, in general, of course, that determines how fast that stuff converges and so forth, okay, to the steady state distribution. Again, also pretty quickly here, we're basically, an important thing, as I said before, what we're assuming is that P is reversible. It has a unique, in our case, unique distribution pi that satisfies this detailed balance condition. Okay, so why is that? Why do we want that? So a part of the construction of the Szegedy walk unitary is, from a slightly more modern perspective, is that you walk through the discriminant matrix. So what is the discriminant matrix? Is you take your original walk that is reversible, and then you multiply from the left with square root of d, from 1 over square root of d from the right with square root of d, where this is just a diagonal matrix that has all the your steady state distribution on the diagonals entries, right? And since this matrix is sort of detailed balance, P is detailed balance, it turns out that this matrix is actually Hermitian, right? So it's a similarity transformation that takes a detailed balance matrix to a Hermitian matrix. And that features prominently in our construction. okay? And so what happens now, what makes this from an algorithmic point of view kind of tractable or interesting, is that for detailed balance matrices, the discriminant actually does not depend on the steady state explicitly at all, because the detailed balance condition makes it fall out. And what you can write is basically that the discriminant matrix is just the product of the square root of these of your transition matrices, and it doesn't have any explicit pi dependence on that. So what I'll talk about a bit, we want something similar in the quantum setting, right? So that's an entry-wise product, Hadamard product of that matrix. And then there's another feature, which also follows immediately by having multiplied with d to the minus 1 or d to the right, is that, that the quantum sample that Pavel also introduced in an earlier talk on Wednesday, which is essentially the canonical way of mapping a classical probability distribution to a quantum distribution by just taking the square root of the weights, adding up only the positive weights essentially, and which is a legitimate quantum state, that becomes an eigenvector with eigenvalue 1 of the discriminant matrix. Okay, fine. And if we now have all these things in place, let's start constructing what the Szegedy walk unitary actually looks like classically. Right, what we have here is sort of, we have to define these kinds of states first. So they're kind of special. There's a tau x, and what you realize, okay, they live on a double state space effectively, right? So originally you had only one copy of omega, but now you have two copies of omega. So they live on a double state space, so if you have the sum over omegas of the x's, and you have the sum over omega of y. And what you do is you basically define states where you say, well, what are the places square root of that I, within the walk, could have transitioned from to get to x? And what I'm going to do is I'm going to just take the square root for some reason out of my transition matrix. So, and if you look at this, this is a properly normalized quantum state, and there's a family of them that are orthogonal. And the other thing that I need is sort of in that construction is just to define a swap operator between those two systems. So I had the original walk on one copy of omega. Now I double the system. I have basically now consider states on omega cross omega, or if I treat this as a Hilbert space, Cn tensor Cn. And so now I've defined these state vectors that live across those two things. And what I'll define now is sort of a swap operator that just exchanges those two systems. Once I have that swap operator, I just take those states and bake them into an isometry, where I go from omega into that omega cross omega space. Okay. So if I do that, why do I do that? Well, there's a neat way I can go and express my discriminant matrix that I had before as basically an isometric transformation of that swap operator. So this is sort of a block encoding, if you will, if you're a quantum person, but it's sort of a T, S, T dagger. That's the entire point. That reproduces, you can check essentially, that reproduces exactly the discriminant matrix. So what does the Szegedy walk then effectively do? Well, it's essentially the product of two reflections. One reflection I'm doing is the swap, which is a reflection by itself. The other reflection is exactly across the complement of that space that I basically trace out with the isometry. So now I have basically two reflections, which define them, and so the two reflections roughly define a rotation. So it looks very Grove-esque in that sense, but this is for a general walk, and so that gives you essentially the walk unitary we want to analyze in a bit. Okay, and so where I said, if you take that out, that T dagger T of the isometry, it's just a projector onto the span of those tau x vectors that I've introduced. So essentially, in a nutshell, what are two things that we basically need? We need a reflection, and we need an isometry. And once we have that, that basically gives us the block encoding of Q. We can construct a quantum walk out of the two reflections from those very canonically. Okay. So, So the first thing is you can check that also if you have the matrix Q and have the Q sample be the eigenvector with eigenvalue 1, it turns out the claim that I made earlier, if you basically go and apply T to the square root of pi up to that transformation, that thing turns out to be also an eigenvector with eigenvalue 1 of the Szegedy walk unitary, if you follow through the steps. right? So we start with the Q sample, apply the isometry. Q sample lives only in one copy of the state. You're now in the double copies of the state, where you basically tensorize those. And of course, this is now, it lies in the span of pi, so yeah, of course, that's invariant. But since this walk is detail balanced, which is very important, the swap basically allows you to just have this also be an eigenvector of the swap operator. So the joint product, fine, is basically now an eigenvector with that one. The other thing is, which I'm not going to go through in detail, is the relationship between the spectral gap and the phase gap. Right? So the original spectrum, say, was the eigenvalues of the Markov chain P. And that's the second one is your gap, roughly. And what happens now with the unitary is something interesting. You basically lift that spectrum to a unitary spectrum, and you can very much relate the spectrum of the unitary to the spectrum of the walk. And you realize that the phases roughly are e to the plus minus 1 I r cosine of lambda j. I'm wondering, what is an intuitive reason you can think about this as sort of, I don't know if you're familiar with either the PQ lemma, or you can think about this in terms of singular valued SVDs, or basically canonical angles between subspaces. Roughly, that's the game that's playing here. You have basically two subspaces, and they have relatively many canonical angles, and they're constructed in such a way that their overlap basically reproduces the matrix Q. And what you find is that, well, there's a nice basis in which you can work that then basically gives you that these canonical angles that you construct this way basically relate to your original eigenvalues this way. And if you just plug that in, you realize, okay, this gives me the square root speed of delta in the phase, okay? Right. So now in a summary, what we have is now what we need is we need an isometry, we need a reflection somehow, and then we need to cook that up into a unitary, and then we basically get all those desired features and properties. And what we want to make sure is that the isometry and the reflection play together so that if you multiply them out together, you basically end up having the discriminant matrix. Okay, fine. So let's look at the Szegedy walk unitaries for Lindbladians and how you could potentially get that. Okay, so when we start looking into this, there are various proposals of how to do that, and so a lot were really tied to many classical aspects of the walk, where you define a particular basis. In that particular basis, you try to set up a Szegedy walk, essentially, in that basis, and just try to find some unitary transformation. That works if you can identify the eigenvectors uniquely with by their eigenvalues, then that basically works. But in general, we wanted something that's sort of more structured in the entire thing and feels right, right? And why is that interesting? Well, you see a lot of structure all of a sudden, so that's always interesting when you want to design algorithms. And ultimately, the hope is maybe that's actually useful in the context of an algorithm somewhere, because you have all these features, but now for quantum Hamiltonians that Szegedy walks give you. Okay, and here also we look at the standard canonical setting. We look at generators of a semi-group. We assume it has a full rank fixed point, so it's primitive ergodic, if you will. Again, we assume that the spectral gap determines now convergence in some loose sense. And yes, so let's try to reproduce all those things. And what was sort of inspirational slash got us started in actually trying to go down that path to see whether there's some structured form in which you can actually find those was a result by Carlin and Maris, where they basically go and classify the form of all GNS detailed balanced TCP maps. And if I'm speaking very loosely, it basically means they all look kind of like Davis generators. So it's very helpful for us to basically just focus as that on the canonical example, and everything else is sort of embeddable into that thing if you want to have some minor algorithmic changes. Right, so here I don't need to present what the GNS inner product is and so forth, but that was the starting point. So what we needed in some form is the specific form that the sigma GNS balanced maps have, and start building our reflections and all this stuff based on that. Right, and so there are certain properties that you have exactly that you want that sort of like a Davis generator or generally sigma detailed balanced or GNS detailed balanced Lindbladian basically has the property that these jump operators happen to be eigenvectors of the modular operator. And there's a feature that we need later in the construction is that there's this pairing between those two operators. So there's a pairing of an operator Vj to its partner V dagger J. So they occasionally can be the same, I guess, but sometimes you have this pairing between a J and a J star, and there's always two of them. And that's sort of a very central ingredient for us in constructing the corresponding walk, okay? So now we have to go, and sorry, going pretty fast. Okay, now we have to go and construct a quantum discriminant. Okay, so the canonical way is exactly, yes, we take the inverse of an inversion. I don't actually know whether that has a proper name. So multiplication, non-commutative multiplication by sigma. That stands in as sort of our diagonal matrix D. We take a root to the right, 1 over root to the left. So canonically, well, that's immediately the generalization of a quantum discriminant. And it turns out, yes, that's Hermitian relative to standard Hilbert-Schmidt inner product. Immediately, okay, that works. So that's a Hermitian matrix. However, what you see basically is we have the same features. So they have P and Q as maps. They have the same spectra because it's just a similarity transformation. And I don't know whether I would talk about this as a fixed point, but sort of the eigenvector, quote unquote, with eigenvalue 1 is again the root of your density matrix, which by itself is no longer a properly normalized one. But if you just plug it in, yes, it comes out on the other end. So which is very analogous to basically what you have classically. Okay, we're comfortable with that. Let's do this. And however, it turns out for us, structurally, it was easier to really work in that Lindblad picture where you have this entire characterization. So we go and make a slight tweak and say, well, what we're going to say is we're going to demand that we normalize that properly so that sort of the operator norm of the Lindbladian is bounded by 1. So so we can algorithmically achieve that by ensuring that sort of the coupling operators happen to be reflections. Okay, we'll talk about that in a bit later. But once you do that, we just do something like a rough, dirty one. We go into the continuous time picture, and then say, well, we're going to call this the discriminant. It's identity plus the Lindbladian version of what we were just doing. Okay, which is fine. This still has a positive semi-definite spectrum because of that constraint. So we're just going to work with this one, and we're going to call this our discriminant for now. So we're sort of now switching into the continuous time picture because there's more stuff we can basically piggyback on. Okay, now there's like a first-year grad student math trick that everyone uses when you work in quantum information and finite spaces. You always do these vectorization tricks. So you basically column stack essentially operators by just flipping the bra into a cat on the second side. And then you basically now turn vectors into matrices. And that gives you sort of a very natural isomorphism between C n cross n into that double space Cn tensor Cn. Okay, fine. And so we work with this that has a couple of properties. So if you do that, then you basically have the rule that AXB just turns into A tensor B transpose acting on that vector. We'll need that. It's also a very well-known trick. And if you start with a linear map essentially on that space, you can immediately associate sort of a headed map on that tensor product space, which respects that isomorphism, if you will. Okay. And typically, I don't know, I remember I used that a lot for various proof tricks, and it's a lot nicer to think about these in terms of matrices as opposed to operators and so forth. But that's kind of interesting in our construction because it naturally gives you what you effectively want for an algorithm later, right? So obviously, Q and Q perp have Q and Q hat have the same spectra. And there's also tau hat, which is now sort of the vectorized version of sigma that we have. And that's sort of the unique fixed point of Q hat, right? And if you look at that tau hat, that turns the entire thing into a pure state. And if you write that pure state in the energy basis, it looks like this, which is sort of what physicists refer to as the purification, a particular kind of purification of your fixed point density matrix. So that comes out quite naturally. So I think some people call it a quantum double or whatever. So, but it's just a very, very natural purification of your original density matrix that you consider. Okay, and so yes, naturally it also lives on a tensor double space. And that comes automatically out of this very simple initial mapping between Cn cross Cn to C tensor n, Cn tensor Cn, right? Okay, so now let's look at what we actually want here. So this is actually the discriminant we want to work on. So this discriminant, our discriminant has to somehow be a block encoding that lives on that doubled Cn tensor Cn space. And in order to construct a Szegedy walk for this entire thing, we need to go back and find an isometry and a reflection that does that for us, right? So once we have an isometry and a reflection that gives us the block encoding of that thing, we're peachy and fine, okay? And again, that ensures, if you then do the standard trick, reflections times 2 pi minus I, that that sort of this purification happens to be the fixed point of your original Lindbladian, and it happens to be the fixed point of our reflection. And what we want is then what immediately also follows by the same arguments of the block encoding, or essentially, yes, this PQ lemma, is that you have this amplification of the spectral phase gap. So all we have to do is find a T and an R that gives us that. And then we're essentially in business. So what we want, though, more from an algorithmic point of view, we want to be able to sort of have a way of you giving me a sort of a quantum map, and then find an actually unitary circuit that is sort of efficiently implementable on a quantum computer that does all that, because otherwise it's not an algorithm. Okay, and then more importantly, what we want to make sure is that we don't want to go and have to know what the spectrum of the Hamiltonian is explicitly in order to construction. So we would like to have some form of an analogy to see that basically, okay, our discriminant classically was basically the square root of that Hadamard product, and that doesn't depend on the fixed point at all. In the quantum case, it's even more painful if it were to depend on the fixed point, because we wouldn't even know the ratio between them, because we don't have access to the spectrum. So the construction basically has to explicitly not depend on that fixed point. Okay? So, since we know basically it's fine to just consider Davis generators, that's what we start out with and play with a little bit. And just a brief review. So what we have is basically your Davis generator. Okay, there's a spectral decomposition that we work with, that we care about the Gibbs state as the normalized trace of e to the minus beta h. So what's the form of the Davis generator that Davis generators we're going to use? Well, so the jump operators, the Lindblad operators are these S omegas. And they basically just take out the transitions from energy space PL to the transition energy space PK for all the allowed energy pairs that correspond to omega. And it has this pairing that we talked about beforehand, where you say you have, if you dagger it, you basically match to the star to J, so J star. So V dagger J is the same as V J star. And it has this particularly nice property that you basically get to push the Gibbs states through and only pick up an e to the minus beta, well, energy, e to the minus beta omega in that setting, right? So that's sort of, those are the features where this entire general structure becomes manifest. And what we also need is sort of a filter function, right? So that that has also this pairing property where g to the minus omega is e to the minus beta omega g omega, okay? So if you stick all that together, you end up with a Davis generator, right? So the Davis generator in that case is basically the sum over those Bohr frequencies, that filter function, and so forth, where the local one just looks like that. And yes, what you can show is that, okay, that the Gibbs state happens to be the steady state of this thing. And if we're choosing reflections actually as alpha here for the coupling operators to Bath, if they generate the full matrix algebra, yes, then you have a unique sigma. Okay, we're all peachy. So now let's, for a second, briefly review the most fundamental ingredient in many quantum algorithms, which is phase estimation, quantum phase estimation. So what is quantum phase estimation from a very high-level perspective? It's just basically an algorithmic implementation of a von Neumann measurement. That's all what phase estimation does. So I have some large, complicated observable on the system, which in this case is the energy. And then I have a pointer register, which basically tells me where I am. And now I jointly evolve them by h tensor p where this is actually the physics momentum operator. And what it does is basically, if you expand that, e to the minus h tensor p is basically, yes, you have the sum over all those eigenvectors, and now basically in the phase of the momentum operator, e to the minus, well, that's effectively a push, right? So this is, I don't know, the push that basically starts translating stuff on your pointer register. That's roughly what's going on. So if you come in with an eigenvector of your Hamiltonian and have the pointer set to 0, then all it does is basically, that's an eigenvector, so you replace h by its eigenvalue, and it just basically pushes the eigenvalue into the pointer register, and that's how phase estimation works. That's all it does. Okay, and so how do you implement that algorithmically? Well, you discretize everything, right? So you do a discretization. What you do is you basically model your pointer register by an r-bit integer. Then you go into the momentum basis, so Fourier transform. Then your standard p hat in the Fourier basis is sort of diagonal, and you just count the bit values. And if you plug that together, and if you say, well, I first have to do a Fourier transform, in the case I know I'm coming with 0, so it's fine to just do Hadamard's, then I do this evolution condition with different bit values, and then Fourier transform back, then I have effectively implemented the von Neumann measurement, which is a phase estimation. Okay, so here's the biggest crux in that construction from algorithmic point of view. What we do in our analysis is we cheat a little. We're going to say, oh, this is happening perfectly. We're just going to ignore for now, for the discussion, that there's actually a finite discretization error when you do that. And we say, well, we look at a bit at the idealized version. That's very boundable and whatever. And so what we do here is basically say, well, in the idealized version, your phase estimation on unitary is exactly sort of the projector pi j on your energy state, and you basically come with the vector x to x plus epsilon. So this is what is actually most of the algorithmic advances basically is that, yes, that's dirty, you're not allowed to do that. We'll do it anyway for now, okay? And but that is sort of a crucial ingredient for our construction. So now, recall what we want to do is we want to construct a isometry and a reflection, basically, that gives us Q and gives us later on the Szegedy walk, okay? So let's look at our construction. So what we do is basically, we somehow want to recover basically these S omegas. And so what we do is basically in that construction, we construct two isometries. So we have, recall we have basically a register with the original state, and then you have the tensor other Cn register. Those are the two registers because you're now living in a double space. What we need is we need a pointer register, and we need a way of somehow implementing the filter, the rotation. So what we do is basically in that setup is we do a forward evolution with a phase estimation, kick it with a reflection, do a backward evolution, and then based on, then in the ideal case, what you have in this registers are the Bohr frequencies. They're stored in that register. Based on the Bohr frequency, you basically implement some rotation related to G omega. And you do that for one copy of the system that is sort of real. And then that vectoric basically demands that you complex conjugate, if you will. And then we basically do the complex conjugate evolution on the other register. In both cases using the same frequency register. So we didn't know what that was, but so we learned now this is called an operator Fourier transform that you do that gives you access to these S omegas. Okay, so fine. Now if you have those two little independent isometries, we have to, wait, I have to define what the filter rotation is. So the kick, as I said, is just a general reflection operator. So if you have sufficient, you could think about them as Pauli's, if you will, or other things. If you have sufficiently many that they generate the entire algebra, yes, you're fine. You're unique. And the filter rotation does the following. So in the frequency register, you basically condition on what that value is. And based on that, you basically say square root of 1 minus the G omega or square root of G omega. That's a sort of a unitary rotation on that filter register. So once you've cooked that up, you basically want to bake that together to the full isometry that we work with. And so what we have to do here is basically we have to distinguish sort of a little bit between the non-complex conjugate and the complex conjugate copy. So the first copy, the second copy, and because they have to be swapped and intertwined in a certain way between each other. And then you want to add them in a particular way, which means you do a conditioned or anti-conditioned application of those on the plus state. So that gives you this, algorithmically gives you this isometry. So that is our isometry. Well, that's how we define it. The other thing is now we define a reflection R. And that reflection basically does the following. So we had this additional add bit for here. We have filter frequency system 1, system 2. And conditioned on that filter, we do the following equivalent of a swap. And so what the swap does is it associates a Bohr frequency omega with its partner Bohr frequency minus omega. The conditioned X is basically just to get the copies right to line up. So, but if you can check, that is of course, that's a diagonal, that's a reflection. The condition C0 is also a reflection, and everything else the identity. So this is actually what we cooked up for R is actually a reflection operator. And so if you work that out a little bit, you see what the isometries essentially look like for T0 and T1. It has basically one copy of the operator Fourier transformed reflections that you kick the system by, the conjugate copy, and on these store the corresponding ideal Bohr frequencies. And now you basically have in the top register, you basically have this condition, this rotation that gives you this state, right? So that's our isometry. The reflection looks like this. So we have, if on that condition nothing happens, you don't do anything. But once you basically choose that you actually want to reflect, and that's part is you associate these partners, omega to minus omega, and you flip T0 and T1. Okay, so that gives you sort of a reflection and an isometry together. And good. If you now sit down and work out what Q hat does, if you do a T dagger RT, you end up exactly with this form. So you have an identity plus a G omega, G minus omega, S omega, and then, because you swap those S omega, S dagger omega. And to the other case, you basically have this guy, and you basically meet these partners. And that turns out to exactly be the quantum discriminant. And again, a nice feature of that thing is that doesn't explicitly depend on the fixed point here. Maybe did I talk about that earlier? I don't know. But that doesn't explicitly depend on the fixed point because of the properties of G omega. So you just have the square root of these things together. Okay, so that's our desired quantum discriminant, and which means, yes, we now have a Szegedy walk, actually. Because I have the reflection, I have the isometry, and now we do the same game, and you recover all these same properties that you have before. Okay. So let's make some small observations before we go on, because I added a few slides based on some discussions that we had during the conference. So what you can think is now we basically have the same setup as with the classical Szegedy walk, and you have it for a thermal setting. So you could actually now think about preparing as an application. You could think about preparing the purification at some desired temperature if you have some annealing schedule. That's usually what people do, and it works exactly the same way in the quantum setting as it works for the classical setting. What else does that give you? Well, it gives you an algorithmic implementation of the Davis generator on a quantum computer with like a little asterisk here if you ignore the complete complexities that come from actual phase estimation, right? And because that's where the entire algorithmic challenge later sits. If you actually want to implement that, you have to worry about finite discretization errors in phase estimation. If that wasn't the case, this would look peachy. And yes, you can use this as a building block in other quantum algorithms. So that said, what we did in the paper back then is sort of, we know that this is not how phase estimation actually works. Phase estimations has basically finite rounding errors and so forth. And what we did is we sort of took the cheap way out and said, well, we're going to look at only Hamiltonians that satisfy something that's called the rounding promise. So what is the rounding promise? Is basically you exclude certain intervals out of the spectrum that the Hamiltonian has. And once you exclude those intervals, basically, things become a lot nicer, because in that case, you exactly recover actually that map that we have with a slightly wrong Hamiltonian that you're actually starting to implement things. But the entire argument goes through as if it was ideal phase estimation that you're considering. Right? But the problem is, of course, that's not really what nature gives you. So that's rather unphysical and so forth. And at that point, we discussed, Pavel and I, our concern was whenever we now go and try to look at more physical phase estimation, there's going to be perturbation bounds and so forth, and they're probably going to depend at least at one first order on the gap of something. And if your entire advance is basically, oh, we just want to map gap to square root of gap, there's not much value in trying to do that. And we figured, okay, fine, we'll just assume the rounding premise and be done with it, because it's structurally sufficiently interesting, right? Which immediately then asks the question, so can you actually get that to work for a physically relevant and correct Hamiltonian? And the answer is possibly the result that everyone knows now, CKG coming to the rescue. Because that is very much attuned to the fact that you have finite and incorrect phase estimation. And so that's the result that I'm assuming everyone is familiar with. And you can ask basically, where does that actually differ in our construction from a Davis generator structurally? And so one place where this differs is sort of, is that you now picked up a coherent term that makes stuff detail balanced. The other place where it differs is sort of our operator Fourier transform was completely flat, but they introduced a Gaussian. Okay, so those are, from an algorithmic point of view, okay, that's stuff you have to worry about. But if you check, you still have this nice pairing property in that case as well, right? Although it's a bit weird because this is KMS detail balance, right? So in our entire construction assumes, oh, we work with this G and S detail balance normal form, but their construction is a KMS thing. So can you get the KMS thing to fit into the GNS thing in the algorithmic construction? And the answer, well, I don't know. It's an open problem. Might be an interesting one because you might see something structurally. But there's actually hope, I think, because the construction is not too different and not too far off from basically the GNS type construction. So if you look at sort of, let's look only at one copy of that isometry that we're considering and dig in a bit more deeper into the structure. So if you start removing one system register because you only care about one, in this case, let's just look at the algorithmic implementation and write out all the components. One thing where this differs is specifically, yes, they rather than having the flat thing from our initial flat Hadamard, which just gives you the uniform of the spike, what they have to construct a prep F, which gives you basically this Gaussian envelope rather than the flat one. So that's structurally different. But the overall form is not too different, so you might have hope, well, maybe you can piggyback on that old construction. So you could, rather than do this as an isometry, maybe you can do two copies of those isometries. Cool. And then if you look at this, so okay, if you bag that together as an operator Fourier transform, the entire thing is not too far off of what you have to do to basically to get the CKG one. So you have to modify the isometry essentially with the Gaussian envelope, but then at that point they basically cut off and do something different. But maybe you could think about, maybe I can insert a reflection here somehow and work with that. But okay, so what they do is they undo the operator Fourier transform, but there's a new part, and that's essentially something that Andras mentioned on Monday, to sort of take care of that Hamiltonian contribution in our old construction seems to be difficult, or seems to be tricky and challenging. So because this is the other component where actually that you really need to make this thing detail balanced, that isn't there in the old construction, and so we don't immediately know how to basically lift that into an isometry and a reflection the old way. But yeah, that might be an interesting thing to think about. And you could wonder, maybe there's something as a structure that you can analyze that's probably a bit more general and high level, depending on how things go. And yeah, I think I'm at this point I'm done. Right, thanks.